Hi, this is an example problem that has to do with understanding the nomenclature of images. This is for a mirror, but the same words and terminology apply to lenses as well. All right, so what we're going to do in this problem is basically verify the picture that we see here and understand how we can characterize an image in terms of the distance of the image, magnification, orientation, and image type. All right, so first of all, distance. The edge of the mirror here, this is always the reference point for measuring distance. So for the object, for example, from here to here, that's your object distance. And then if I want to measure the image distance, it's also a line that begins at the edge of the mirror. So we can call this the DO, object distance, and this distance here, this would be DI, the image distance. And we can see for a plane mirror that we have a lot of symmetry here. We can tell that already the distance on either sides of the mirror from the object or the image is the same. We also have a set of equations that allow us to relate object distance, image distance, focal length, things like this, and we're going to look at that. First, I want to show you quickly just that this really is, though, just based on geometric stuff, and so we call this geometric optics. And so if we have, for example, take the lower ray here. This is our incident ray, and it makes a certain angle, theta I, incident with the normal line. This is your normal line here, to the mirror surface. And if we look and see what is the outcoming ray, or reflected ray as we call it, theta R, it makes equal angles with the normal to the surface of the mirror. That's just the law of reflection. So this is all based on the law of reflection. However, we're not going to use that when we actually solve image problems. We're going to use the equations. So just a few more things. When we talk about magnification, we're talking about how tall, in a sense, the image is compared to the object. So if we look at the height here of the object, call this h0, how does that relate to the height of the image? Well, again, because of the nice symmetry of the plane mirror, we can see that they're the same. Well, let's go and look at the equations we're going to use for solving some of these things. So this is a note sheet with equations, and you can see that these equations come from geometry, but we're just going to focus on these two equations, the mirror equation and the magnification equations. And the same set of equations will apply for lenses as well, but we will have to use a separate set of conventions for the signs of what's positive, what's negative. And so we're going to go ahead and look at that. Let's go ahead and first copy these equations over to our problem. So here we have our equations, and in part A we're asked to calculate the distance di. And we're going to use the mirror equation here. Now for the mirror equation, we are told the object initially is a distance 0.5 from the plane mirror. So we know that this is a length of 0.5 meters. But we got to figure out what is the sign, is it plus or minus. Let's go back and look at our sign conventions here. So right below here. And the way this works is you have a front side here and you have a back side of the mirror. If the object, the image, the focal length are on the front side, they're all positive. However, if they're on the back side, they're negative. And you'll notice a distinction between concave, where they're positive for these things, convex, they're negative. But here we're looking at a plane mirror, and so what is the focal length, plus or minus? Well, we're going to calculate that first. So for any type of mirror, the focal length is equal to the radius of curvature of the mirror divided by 2. However, this is going to be absolute value, because if we look back at the sign conventions, focal length for a convex mirror is plus, for a negative. For a concave mirror, it's positive. What about for a plane mirror? Well, we got to think, what is the radius of curvature? Imagine you have a circle, and so here's your radius. It's from the center, and this is a portion of the mirror, right? It's curved. What if we start to get a bigger and bigger radius? Eventually, a flat mirror, this radius here, for a plane mirror, it's going to be equal to infinity. And so we can actually put that right into our equation here. For a plane mirror, the focal length, well, infinity divided by 2, it's just simply infinity. So this is for a plane mirror. Do we need to worry about the plus or minus? Turns out it doesn't matter. Plus infinity, minus infinity, basically the same thing. So we know what the focal length is. We know what the object distance is. Well, we didn't check the sign yet, but if we go back and look, the object is in the front of the mirror. In fact, objects for mirrors will always be in the front, because if you're in the back, you can't have any reflection. The surface is on the front. So DO is positive. And now we can go ahead and use this. So this is a positive value, to go ahead and calculate the value for DI. So let's use the equation. I'm going to go ahead and write it. I'm going to do it in a slightly, just switch the order. So 1 over DO, or plus 1 over DI, equals 1 over the focal length. And first of all, I'm going to go ahead and just put in infinity. Now, if we were worried about the infinity, yeah, we are usually sometimes, but 1 divided by infinity, what's that? That's always 0. So this works out pretty nicely here. And if we want, we can do one more step here. Let's 1 divided by DO is equal to negative 1 over DI. Now, for this particular one, we can take the reciprocal of both sides, and we'll see that the, I guess what I wanted to do here actually was solve for DI, right? So let me just reverse these real quick. DI is equal to negative 1 over DO. And if I take the reciprocal of both sides, in this case, it tells us DI is equal to minus DO. And we know what DO is. So it's going to be negative, and then we have, for DO, 0.5 meters, and that's going to be equal to a negative 0.5 meters. So that's our DI here. And that tells us that the height is the same at 0.5. The negative sign here, this guy tells us that the image is in the back. All right, let's go into part B here. So for part B, we are asked, what's the magnification? Calculate M. We've got 2 ways to do it, but we know DI and DO, so we're going to use this equation. Minus DI divided by DO. So that's going to be a negative. DI is minus 0.5 meters, and DO is 0.5 meters. The negatives cancel, and this is just going to be equal to plus 1. And so that's our magnification there. Now the sign of the magnification and the magnitude, the number, both have a meaning. So we've been asked here in part B, is the magnification enlarged, diminished, or the same size? Usually we think of magnification as getting bigger, but in this, it actually can be smaller, same size, or bigger. And so we're going to use either of these 3 possibilities. Now for this one, because we've got the 1.0, that means that they have the same height, same size. So this is going to imply that we've got image is same size as object. And that's exactly what we saw when we looked over here and kind of compared the two, right? Now the plus sign means something else. Looking at part C here, we are asking, what's the orientation? Is this thing upright, the same as the object, or is it inverted? Has it been flipped upside down? Well, clearly we can see that it's upright. So the crown's on the top here, it's on the top here. That means that they have the same orientation. So I'm going to write that down. Same orientation. Now we can also see that directly from the magnification. So when the sign is a plus, that indicates that it's the same orientation. If the magnification has a minus sign in front of it, that indicates that it's been flipped upside down, it's inverted. Okay, finally we've got one more question here, which is part D. What is the image type? Is it real or is it virtual? Well, they've told us already this is a virtual image, right? How do we know that? Well, let's look at this picture a little bit more closely. Check out the eye over here. The eyeball is basically seeing some rays come. They approach the eye and they kind of spread out, right? So what does the eyeball think? Human brains are designed to believe that light always travels in a straight line. So it's going to trace these backwards to a point where those two rays converge. And so the brain thinks that there's an image there. It thinks that that's where the rays that get into the eye are coming from. However, we've dashed these rays because there really isn't any light there. It's all part of the mind's illusion. And so this is not a real image because we don't really have light coming from a point and spreading out from the image. That's not really there. It's all an illusion in the brain. Therefore, we call this a virtual image. And again, the check is look and see, is there really any light coming there? There isn't. Therefore, this is virtual. So I've gone ahead and written that down. It's virtual because there's no light traveling from the image to the eye. There's another way to see that though too, because we found out that the image is negative, right? The image distance negative 0.5. And because of that, we know it's in the back of the mirror. And of course, behind mirrors, you don't have any light anyways. So for mirrors, if you get a negative image, and you know it's going to be negative image distance, virtual image. Now this example problem really is the good one to see at the beginning, because as you go on and solve problems, peer review problems, homework problems, you're often going to be asked to characterize the image based on these various properties: distance, magnification, orientation, image type. Whether you're using mirrors or lenses, all of the images can be characterized by these same 4 ways.